Welcome back to the class on electromagnetic field theory. In this lecture, we are going to discuss about force on a moving charge in a magnetic field. First, we are going to discuss about the force on a differential current element in a magnetic field. Differential current element is nothing but a small conductor in which the current is passing. That is nothing but a differential current element. If it is placed in a magnetic field, how much force is experiencing on a differential current element? That we are going to find. We know that there is a differential force on a moving charge in a magnetic field. dF bar equal to dq into V bar cross V bar. V bar is nothing but a velocity of a charge. V bar is nothing but a flux density of a magnetic field. We know the relation between the current density and a volume charge density. J bar equal to rho V into V bar. Again, V bar is the velocity of a charge. Rho V is nothing but a volume charge density. J bar is the current density. Now the differential charge we can write it as a rho V into dV. Rho V is nothing but a volume charge density. dV is nothing but a differential volume. Now substitute the equation 3 in a equation 1. In place of dq, to substitute this equation, we are getting the fourth equation. dF bar equal to rho V into dV into V bar plus V bar. We know the J bar equal to rho V into V bar. In place of rho V into V bar, we substitute the J bar. We are getting the differential force equal to J bar cross V bar into dV. This is the differential force if volume charge is moving in a magnetic flux density. Suppose the sheet charge is moving in a magnetic field, then there is a some amount of force. The same manner, the line charge is moving in a magnetic field, there is some amount of force will be experiencing on a line charge. So to find the force on a differential sheet charge and the line charge, we know the relation between the J bar, the K bar and I bar. K bar is nothing but a sheet charge density, I is nothing but a line charge density. Now, in place of J bar, if we substitute the K bar, then this force is equal to the force on a differential sheet charge which is moving in a magnetic field. The dV should be replaced with a ds. Similar manner, if you find the force on a line charge which is moving in a magnetic field means this J bar we have to replace with a I bar. So the differential force equal to I into dl bar cross V bar. Up to here, we know the differential force. If we want to find out the total force means, then we have to take integration. If it is a volume charge means volume integral. The total force F bar equal to volume integral of J bar cross V bar dV. The total force on a sheet charge F bar equal to surface integral K bar cross B bar ds. We are getting from the equation 7. The same manner, if we find the total force on a line charge means the above 8th equation will be modified as a F bar equal to closed line integral I into dl bar cross B. See here why we have taken the closed line integration means the current is passing only when the circuit is closed. Now we are going to find out the force on a straight long current carrying conductor. We are assuming that there is a magnetic field is there whose flux density is B bar. This is a conductor which is carrying a current of I in this direction. Now the force on a current carrying conductor which is placed in magnetic field F bar equal to I into L bar cross V bar, where L is nothing but a length of the conductor. If you find the magnitude of this force, this is the cross product. So we are getting the F equal to BIL sin theta. Theta is nothing but a angle between the flux and charge which is moving in a conductor. Actually, this force will be experiencing on the charge which is placed in the conductor. So, finally, the force will be reflected to the conductor. Force between the two differential current elements. Here we have taken the two current flow. This is the first current flow which is carrying a current in this direction because of this voltage source. The same manner, this is one more current flow which is carrying the directional current in this manner due to this voltage source. I1 dl1 bar is a differential current element on a first ring. I2 dl2 bar is a differential current element in a second ring. R12 bar is nothing but the distance between the first current element and second current element. R21 bar is the distance between the second current element and first current element. When the current is passing through the conductor, there is some amount of magnetic field will be creating. So because of this current element, there is a magnetic field will be experiencing at this point. Because of this current element, there is a magnetic field will be created at this point. So whenever the current carrying element is placed in magnetic field, experiencing a force. That force we are going to find out. The force on a first current element due to the flux creating from the second current element is given by the I1 dl1 bar cross db2 bar. db2 bar is nothing but a differential flux density at this point due to this current element. Now we are going to find out the differential flux density at this point due to this current element from the Bayer-Savart's law. So dB2 bar equal to 1 by 4 pi mu naught I2 dl2 bar cross the unit vector in this direction AR21 bar divided by the distance between the two current elements, that is the R21 scale. Now substitute the equation 2 and equation 1. We are getting the differential force on a first current element due to the second current element I1 dl1 bar cross 1 by 4 pi epsilon naught I2 dl2 bar cross A21 bar R21 scale. Rearrange this equation. I1, I2 are the constant, take outside. 1 by 4 pi epsilon mu naught is constant, this distance scale also the constant, take outside. dl1 bar cross dl2 bar cross A21 bar. If we want to find the total force means I have to take the double integration so that this length as well as this length, total length should be completed. So F1 bar equal to I1 I2 by 4 pi mu naught R21 square, closed line integral of first one, closed line integral of second loop, dl1 bar cross dl2 bar cross A21 bar. Similarly, you can find the force on second element due to the first element. F2 bar equal to I1 I2 by 4 pi mu naught R12 square double integral dl2 bar cross dl1 bar cross A12 bar. The force between the two parallel current carrying conductors. In this case, we have taken the two current carrying conductors. The current passing through the conductors are same direction. Then there is an attractive force will be existing between these two conductors. Because when the current is passing through the conductor, there is some amount of magnetic field is there. In that magnetic field, we are keeping the first conductor. That's why the force will be experiencing. On the first conductor also the current is passing. Because of the current, a magnetic field will be created. In that magnetic field, we are keeping the second conductor. So the force will be experiencing on a second conductor. If this directional current is same, then there is attractive force between the two conductors. If this directional force is opposite, then The repulsion force will be existing between the two conductors. Now we are going to find out how much magnitude of this force. Let's consider the two current carrying conductors carrying a current of I1 and I2 in opposite direction. Nothing but a repulsion force will be existing between these two conductors. The distance between the two conductors is capital R. Now the force between these two conductors is equal to I1 I2 L by 2 pi R capital R newtons. Sorry, this is not D, this is R. L is nothing but a length of the conductor, nothing but this length. R is nothing but a the distance between the two conductors. So thank you very much for watching this video.